A disperse system consists of one component, the disperse phase, distributed as individual particles or droplets throughout a second continuous phase. By rigorous physical definition, a true colloidal dispersion exists strictly when those dispersed particles measure between 1 nanometer and 1 micrometer. This matrix outlines permutations of a dispersed system across states of matter. Coarse dispersions, like emulsions, often exceed the 1 micrometer limit, yet still exhibit true colloidal properties. The phase intersection dictates mechanics. Liquids dispersed in gas yield aerosols, while solids dispersed in liquids form suspensions. Beyond physical state, these systems are categorized by their thermodynamic affinity for the solvent. Lyophilic or solvent-liking colloids disperse spontaneously. Lyophobic or solvent-hating systems resist mixing. Aqueous surfactants self-assemble into micelles, creating stable hydrophilic colloidal dispersions. The specific combination of a material's phase state and its affinity for the continuous medium establishes the baseline thermodynamics of the system. That baseline dictates exactly how much energy is required to force the particles into suspension and what forces will eventually pull them apart. Synthesizing particles within the precise nanometer to micrometer range requires two opposing engineering approaches: dispersion, which shears massive coarse materials down to scale, and condensation, which aggregates individual molecules up to colloidal size. Top-down dispersion relies entirely on applied mechanical force. Colloid mills grind coarse material using extreme shear forces between static and rotating cones. Ultrasonic treatment passes high-frequency waves through a medium, generating alternating regions of compression and cavitation. The violently collapsing cavities shatter coarse particles on impact. Bottom-up condensation relies on chemical supersaturation. By altering the solvent composition or inducing a rapid chemical reaction, dissolved molecules are forced out of solution. Instead of forming a solid precipitate, they aggregate directly into particles of colloidal dimensions. Once formed, colloidal particles must be immediately isolated from unreacted micromolecular impurities. This is achieved through dialysis. Because colloidal particles are too large to pass through regenerated cellulose membranes, establishing a concentration gradient forces the smaller ionic impurities out into the surrounding solvent. By applying pressure, ultrafiltration accelerates the separation, while electrodialysis uses an electric potential to drive ionic impurities across the membrane. However, membrane pore size alone cannot guarantee particle retention. Charged particles often repel the membrane entirely or adsorb directly onto the surface and block the pores. Creating a dispersed system requires forcing matter into a highly unstable state, maximizing its surface-to-volume ratio. Without rigorous purification and the immediate addition of stabilizing agents, those particles will rapidly reassociate to reduce their surface area, destroying the system. This diagram outlines the statistical math required to measure disperse phases, which inherently contain a wide distribution of particle sizes. Determining mass through colligative properties like osmotic pressure yields a number average molecular weight. Conversely, measuring light scattering emphasizes larger particles, yielding a higher weight average molecular weight. These models show that minor deviations from a perfect sphere are quantified as ellipsoids of revolution. Their shape is defined by their axial ratio, the ratio of the half-axis to the radius of revolution. A ratio greater than unity yields a prolate or rugby ball shape. Less than unity creates an oblate or discus shape. In a fluid matrix, these particles undergo continuous, random collisions with the surrounding solvent molecules, a phenomenon known as Brownian motion. This erratic movement drives spontaneous diffusion from high to low concentrations. The exact rate of this mass transfer is expressed by Fick's first law, linking the particle flux directly to the diffusion coefficient mathematically established by Einstein. Because of constant Brownian interference, colloidal particles under 0.5 micrometers in radius will not settle under standard gravitational forces. Stokes' law, which calculates sedimentation velocity based on particle density and fluid viscosity, demands a force far stronger than natural gravity to overcome thermal motion. This equipment is an ultracentrifuge. It subjects colloidal samples to acceleration forces up to 1 million times standard gravity. By monitoring changes in concentration under high radial fields, chemists extract the sedimentation velocity. Under lower fields, they measure the point where sedimentation exactly balances diffusion. known as sedimentation equilibrium. For massive particles up to 1 million daltons, standard colligative measurements like freezing point depression fail. Osmotic pressure provides the only measurable physical effect. Calculating molecular weight this way requires strict mathematical compensation for the Donen membrane effect, correcting for the unequal distribution of small ions caused by the presence of large charged macromolecules. The kinetic equations of diffusion, osmosis, and sedimentation provide a mathematical tether. They allow chemists to measure macroscopic flow and use it to precisely calculate the mass and dimensions of individual invisible particles. This schematic details static light scattering. When light hits a colloidal sol, some of it scatters, causing a visible turbidity known as the Tyndall effect. By measuring the intensity of the light scattered at exactly 90 degrees, chemists use the Debye equation to relate that turbidity directly to the precise molecular weight of the solute. However, the Debye theory breaks down when a particle's diameter exceeds 1/20th of the incident light's wavelength. The particles can no longer be modeled as point sources. To solve this, scientists plot scattering intensity against both angle and concentration on a Zim plot, extracting the particle's shape and mass from the extrapolated intercept. While static light scattering measures the average intensity, dynamic light scattering measures the microsecond by microsecond fluctuations in the scattered light as particles collide in real time. Analyzing these rapid interference patterns yields the specific diffusion coefficient, and by extension, the exact particle size distribution. Direct visual observation of colloids pushes optics to their physical limits. This historical ultramicroscope setup utilized dark background scattering to track Brownian motion indirectly. To see the physical structure of the particle itself requires bypassing visible light entirely, using high-energy electron beams in a vacuum to achieve sub-nanometer resolution. Optical analysis provides a non-destructive method to calculate the exact weight average of a dispersed phase. That precision is necessary because the physical survival of the system relies on the mass, geometry, and electrical charge of those particles. Particles suspended in water acquire a surface charge through 3 primary mechanisms: unequal dissolution of ions, direct ionization of surface groups determined by the pH of the system, or the unequal adsorption of oppositely charged ions from the surrounding fluid. This schematic maps the electrical double layer. A charged solid surface will physically attract oppositely charged counterions from the aqueous medium. The center of these hydrated counterions forms a boundary layer held directly to the surface by electrostatic attraction, known as the stern plane. The electrical potential drops sharply and linearly from the solid surface to the stern plane. Beyond that boundary lies the diffuse layer, where thermal agitation scrambles the ions, causing the electric potential to decay exponentially out to 0 in the bulk liquid. A layer of solvent remains tightly bound to both the ions and the particle surface. The absolute outer edge of this bound fluid is the plane of shear. The measurable electrical potential exactly at this boundary of relative movement is the zeta potential. These diagrams show how the introduction of surface active agents alters this electrostatic profile. Specifically adsorbed molecules can force the stern potential to completely reverse its sign, dropping below 0, or dramatically spike in magnitude, independent of the initial surface charge. The physical distance over which this potential decays is the Debye-Huckel length parameter. Increasing the concentration of background electrolytes in the water physically compresses the diffuse double layer. As the thickness of the double layer shrinks, the measurable zeta potential drops. Chemists measure the zeta potential using electrophoresis. By applying a controlled electric field to a liquid, they track the velocity of the charged particles moving against the stationary fluid. Inputting that velocity into the Smoluchowski equation calculates the precise zeta potential in millivolts. Controlling the specific geometry and potential of this microscopic electrical double layer is the singular lever engineers have to manipulate particle repulsion and prevent a colloidal dispersion from collapsing. In colloid science, the terminology of system failure is exact. Aggregation is any general collection of particles. Flocculation is a temporary, loosely bound, open structure contact. Coagulation occurs when particles aggregate so closely that the system cannot be easily redispersed. Table 5.2 compares stabilizing forces. Lyophilic sols form spontaneously because macromolecular chains unfold in solvent, causing exceptionally low interfacial free energy. They are thermodynamically stable systems protected by thick solvation layers. Conversely, lyophobic sols lack solvation protection, relying strictly on electrical repulsion to survive. The Schultz-Hardy rule dictates that they are exquisitely sensitive to the addition of electrolytes. Coagulation happens rapidly in an irreversible cascade, driven heavily by the valency of the added counterions. Without the natural protection of solvent affinity, a lyophobic system is constantly pulling itself apart. To engineer a stable drug suspension or a commercial emulsion requires balancing the competing forces of attraction and repulsion perfectly. This graph maps the Durjagin-Landau-Verwey-Overbeck, or DLVO, theory of colloid stability. It operates on a single axiom. The total potential energy of interaction between two particles is the additive sum of their electrical repulsion and their van der Waals attraction. Plotted individually, electrical repulsion exists as an exponential positive curve dictated by the Debye-Huckel parameter. Attraction exists as an inverse negative curve governed by the dispersion forces of the Hamaker constant. Adding these two forces together generates the total potential energy curve. The peak of this curve is the primary maximum. It represents the absolute energy barrier preventing the particles from colliding. The height of this barrier is controlled directly by the zeta potential. Further out along the distance axis lies the secondary minimum. At this specific distance, the attractive forces slightly overpower repulsion. For larger particles exceeding 1 micrometer, this shallow energy well traps them in a state of reversible flocculation. Colloidal stability is not a permanent, static condition. It is a highly sensitive state of physical equilibrium, relying on engineered electrostatic forces to hold matter suspended exactly at the peak.